I have been making things for more than half of my life, and they tend to be heavily mechanical or robotics-based projects. A giant Lego Christmas tree on the surface doesn't overlap a lot with what I normally do, but there's actually a huge amount of overlap. There's logistics, there's time management, 3D design, there's 3D printing, all that stuff is the same sort of thing, no matter what you're doing. This video is going to be a technical deep dive, a journey through time from my perspective on making this pretty ridiculous Lego-inspired Christmas tree. I'm going to start by chunking the project into chapters. We obviously need to design the thing, we need to print it, we need to build it. The first thing though is to make a plan. The first part of any good plan is to have a good chat. So I went to Ruth's workshop and we did just that.
Make it bigger.
Make it bigger.
Yeah. Make it bigger. That's the plan, isn't
That's
it?
the plan.
That's the
Yeah,
plan.
make it bigger.
How much bigger?
6 times.
6 times bigger.
We mostly panicked about not having enough time to do this.
To the nightmare before Christmas.
Yeah, but in October, somehow it's still not enough time. We're in October.
Not even Halloween.
No, it's not saying much, but it will be taller than me.
Yes. You're taller than me as well.
We did make some decisions. We looked at the spreadsheet that Ruth had already made and decided what to do with the base. Apart from that, I did mostly just pretty shots of the box. Sinister. It was a good time. All right, I'm back from Ruth's. The main kind of takeaway from an engineering standpoint is we're going to delete the base. The base of the tree is very brown, very big. Honestly, I don't think, or we don't think, especially pretty. That obviously has a huge knock-on directly on the amount of printing, but it's also going to affect the design. So let me show you the booklets I just chucked down. So this is the tree that we're printing. It's the one on the front of the box, and I'll get to this booklet in a minute because there's some very important information at the back of that. In the middle of this tree are some shafts, some like rod pieces, and then there's these brown discs and yellow and grey bits that stack into this sort of central core. The way that that's constructed is with these, as I say, central shaft things that I'm obviously not going to print something of those proportions because that would be crazy. We're going to replace the shaft with steel. But then the way the Lego does it is it has that shaft and then it stacks these sort of brown pieces on top and creates like a larger diameter. And that larger diameter then fits into these pieces, which are otherwise identical to these pieces with a smaller hole. So why not potentially just make that the kind of the main central diameter and simplify the whole center of the tree? I don't know. We'll see what the effect of that is later on. Right now, all I care about is sort of, well, let me show you the booklet because what I care about is in here. In the back of this other booklet is this page. Now this is going to become like my Bible. There's stuff in here that I already know I'm not going to need to do. I don't really have any way of processing this out other than brute forcing it. So sorting them out into piles or spreadsheets or something. I don't know. So yeah. Oh Christ, that's a bit close. Base decision is final. Ruth's going to weld one up. I need to go figure out what the consequences of this are from a design point of view and from a part count point of view and everything else. Keeping track of which bits from the booklet apply to this particular tree, how many pieces there are, and all of that was already a nightmare. There was nothing for it but to do some manual data entry by literally going page by page, looking at the plans, counting each brick, and making a list. I made a spreadsheet, but in reality, Tori made the original spreadsheet. Thanks, baby. And then I copied the data from hers into my slightly prettier one for the video. With details. I made a spreadsheet, but before I show you, past me needs to explain something. If you know your 3D printing, you'll know that the slicer software, which is the software that takes a 3D model and kind of turns it into commands that a 3D printer can follow, gives you a time prediction. You'd think that I should just be able to take that prediction from the slicer, plug that into a spreadsheet, and I'll have an idea of whether there's even enough time to do this thing at all. Problem is, I haven't made any 3D models yet, and I can't afford to wait to have done all of them before I start printing. I need to be printing in parallel, I need to be printing now. My only option is to make some sort of approximation of how much time is involved in spreadsheet form, just so I've got some way of tracking progress. The best way I can think to do that is to use experience. So I mean, looking at this, I know that obviously that part is going to take more effort to print than the small dots, even though there's more of the small dots. If I give each part kind of like a score based on experience, say the big part is an 8 out of 10 and the small one is a 1 out of 10, and then multiply that by the number of parts, I can get an understanding of at least how much work is left once I've started to populate that data into a spreadsheet. The point is, I might be through 3 out of 600 parts by numbers, but that doesn't necessarily mean I'm halfway through the project. I gave myself a list of every part with an image from the booklet, the part number and quantity, sorted by filament colour. I then gave every part that gut feel print time factor I was talking about and actually did the same for the design and my predicted CAD complexity, FAF as I called it. Then, by knowing how many duplicates of each part I had to print and how many I'd done or how far along a model was, I could multiply these values and give myself a progress score for the project as I went. Having any kind of grip on how I was doing in this huge sea of work was really helpful. Okay, we have a grip on how we might simplify the design and we have an understanding of how much work there is. We need to talk material.
Yeah, turn it down to a half.
Is that the 3?
That's the 3 right here.
Brilliant, thank you. Since I would be printing the majority of the tree, the filament was delivered to me. 50 rolls of PLA. At one point I had double the boxes in the house because of a mishap with the filament diameter.
Right, well, until that first batch goes, I've temporarily got like 160 kilos of filament in the house. Thank you very much, Polymaker.
Polymaker PLA makes up the entire tree, mostly Polylite, some Polyterra. It would have been impossible to do this without them, so thank you very much, Polymaker. It seems obvious, but Lego fits together and works because of friction. And the only reason there's friction and not like an impossible fit or a loose fit is because real Lego is a marvel of manufacturing. Engineers and designers at Lego need to hit a consistent design and tolerance for every single part to make sure that every single part is compatible. And we're talking across literally billions of parts a year. I'm going to use the word tolerances quite a lot in this video. If you don't know what a tolerance is, it's just sort of the range of accuracy within which a part is manufactured. Say if you wanted to make it 10 millimeters long, you might say it can be 10 millimeters plus 0.1 of a mil or minus 0.1 of a mil, and those figures are the tolerances. Lego, like this, is injection molded, and that's a process of taking a material, in this case I think it's ABS or some other similar plastic, superheating it, pressurizing it into a mold and basically flowing it into that mold at high temperature and pressure. That way it goes into every single nook and cranny in the mold and can guarantee you capture those details, and it's also very consistent. You can make millions and millions of parts with one injection mold tool. You might be thinking that I could approach this with molding as well. The problem is that making all of the molds to be able to make this many parts. Yes, I've got to make a lot of parts, but I haven't got to make millions. Once you get below a certain number, molding stops being a practical way to do manufacturing because there's a huge amount of work goes into making that tooling, the molds. Even though the tolerances that you can hit with 3D printing are way worse in general, I'd probably have to make the molds with 3D printing, so it would be a completely circular decision, and yeah, I'm going to 3D print everything. Now, you'd be forgiven for thinking, why is he going to model everything himself? Surely those models are available online. Lego's very popular. Loads of people have uploaded stuff over the years on GravCAD and other places like that. But I need the particular ones I need, so finding them in the first place might be a pain. They'll all be designed, or mostly designed, at real size. I obviously need 6x, and there's no guarantee that once I scale anything that I found online up, it's going to fit together. I just talked about tolerances. There's no way that that's going to fit together without a huge amount of effort with 3D printers in terms of prototyping everything, checking it all fits. I don't have time for that. It's faster for me, as someone who's been using CAD for years, to model everything from scratch. I got to work modelling the simpler bricks first, because I knew that I could be printing those whilst working on the more complicated and weird models that are less duplicated as I went. The most important thing here is achieving that same friction fit that real Lego has, but on a large scale. And at this point in the project, I was pretty terrified of actually achieving those tight tolerances. The difference between something that just falls apart and something which doesn't even fit together is plus minus not very much, 0.1 millimeter, 0.2 millimeters at most. And hitting those tolerances with 3D printing, especially big, chunky prints like this, is not necessarily easy. From a CAD point of view, it doesn't make sense to start anew every time. You can take an existing shape and then, use a lot of that geometry again to make another one. So I did that a lot throughout the project, where if there was a square, chop a corner out, suddenly you've got an L, more or less. I didn't have to start everything from scratch every time. And throughout that process, I was kind of mentally building this design language or design consistencies that I was recognizing as I went, that meant I could kind of shoot for a final part every single time. I didn't have to test print everything, and that was critical obviously from a time point of view. But it was quite satisfying because I could make a shape, print it, and be pretty sure it's going to fit first time. This is a bit of a spoiler for the printing part of this video, but obviously that didn't work every single time. Some of the stuff was pretty tight. Also, if you know what you're talking about, you'll know that PLA, which is the material that we're using for this, has an effect called creep or plastic creep. Basically that means that when you put pressure on it, it actually kind of conforms to that pressure over time. So something that is tight may no longer be tight in, I don't know, X amount of time in the future. Despite that, PLA is pretty much the only viable material for this from a cost point of view. So I just made everything a bit tighter than it probably could have been, just to err on the side of caution so that this thing doesn't fall down in a month or two. I need to stop doing that. I keep test fitting things and forgetting that I made this all like permanent fit because we don't want the tree to fall down in Ruth's living room. Cool. 1. Literally just scale everything up. It works surprisingly well in the end. Use calipers, go to 2 decimal places. 2. It turns out Lego's pitch, or the space between pegs, is 8mm, which means at 6 times scale it's 48mm every time. 3. Pegs are 29.4mm in diameter every time. 4. Walls are 9mm wide every time. You can see a pattern. The Lego designers are smart. Be smart. 5. Don't copy everything. There are details in there that you don't need for 3D printing. Keep things simple. 6. Your 3D printer can bridge gaps. You don't have to use support material for everything. Most of the design work was honestly a bit mundane. They're brick shapes, but some of the parts are more interesting. The heart, for example, is kind of low poly style, and the model for that was this kind of mess of surfaces and everything else, but that was cool. Never actually printed those myself. It's one of the few parts that I didn't get around to. Ruth took those on, so I never actually kind of got to see them grow. I also used the oldest trick in the book for the candle flame. I took a picture with my phone with a scale reference, imported that into CAD, and traced around it to get the shape right. So some of the stuff was more interesting, but in truth, it was just a matter of getting through it. There was a lot, but I did it. I need to show you my candles. This is one of the tea lights that Ruth bought on Amazon. Inside is an LED and a little, I assume, infrared receiver. It's actually pretty ingenious how they've done this. Let me pop it apart, and that's what you see inside. If I pull the legs of those components straight, pull through the LED. There's also this guy in here too. Yeah, the way they've done the switch is hilarious. It flexes the leg of this component. It's hilarious and brilliant. We need a solution fast for making something light up on this tree. We've reduced the scope to just the candles, the flames on the candles, because that makes sense. Trying to figure out how to do that using these components. There's got to be a simple way, and I think I've come up with it. The candles on this tree look like this. They are 2 parts. They've got like a white part and the flame, and they come apart. This dodgy looking print, because I printed it super fast, is kind of like the top section of this candle. I thought, okay, well, there's got to be a way of making the switch be removing and putting in the battery, right? On the side of this is this nifty little drawer, and I've added some little grooves in the side of it for fingernails to grab it. Now, if I take the legs on the one side of the little receiver thing and slide the LED into the right place so the other leg's making contact, there you go. I have light. I figure there's got to be a way to recreate what I'm doing with my fingers in a 3D print. Now you understand what this part is for. First thing is to take the battery from the original tea light and stick it in my little drawer thing with the world's most satisfying snap. Stick that in place, and then I'm gonna thread the legs, the same 2 that I used a minute ago, into little slots I made in the print. And then basically the idea is the legs in there are making contact on the battery. Then I can slide the LED into the other 2 slots. There you go. There you go. Little LED tea light thingy. Sitting inside the right diameter for the candle, because yeah, I haven't explained. That diameter difference is enough to break the scale rules, and I can't handle that. This again is a very rubbish print, printed too quickly for this filament. It's flickering because it has a flicker mode, not because the connection is dodgy. And it does have this slot in the back, which is this sort of switch. Let me show you that. How cool is that? Amazing. I am currently in a tiny converted Northern England coal chute cellar. It's like 2 by 3.5 meters. And down here, I've got 3 3D printers that are actually in use, technically 4. I've got the Bamboo X1C, the Bamboo P1P, the Bamboo A1, and technically a Prusa Mark II in the corner from like 2016. It's doing its best. Now, I needed to print fast, and whilst I do have 3 very fast printers, I'm actually limited by the flow rate of the PLA, literally how fast it can be melted through the nozzles is my limiting factor. 3D printers normally use a 0.4mm nozzle. That's what is completely standard. If you buy a 3D printer today, 99% of the time it'll ship with a 0.4mm nozzle. The nozzle is literally the bit that the plastic is melted through, and 0.4mm gives you a nice balance of not being too tiny and not likely to clog too badly if there's anything in the filament itself or anything like that, but it also gives you a good amount of detail. 0.4 is just sort of what the industry has settled on. Let me stop crouching like a weirdo. I could use a 0.4 nozzle for this as well, for the whole tree. There's no real problem with that, but I think there's a level of detail with a 0.4 nozzle that I'm never going to need to hit, or at least for the vast majority of these bricks. They are big, simple shapes. They're rectangles largely. Why would I bother with... It's kind of like using a super fine marker pen to paint the wall. Like, you can, but you're better off with a big fat brush. I'm going to use a 0.8mm nozzle, twice the size. A 0.8mm nozzle in this case has a couple of advantages. One, I can flow the plastic through it slightly faster, and if you know, not an awful lot faster, because I'm actually limited by flow rate, not the size of the hole in the nozzle. The other benefit is strength. Parts with a larger nozzle are generally stronger. This tree has got to be big, it's going to be chunky. It's obviously, we're not like trying to hide the fact it's 3D printer or anything. I quite like the idea of having big fat layer lines, and the texture that's going to give across the whole build, I think it's going to be pretty cool. I'm going to stick one of these 0.8 nozzles in all of my printers. Yeah. The slicer software I'm using for this project is called Orca Slicer, and it's got fantastic profiles built into it for 0.4mm nozzles, but not so good for 0.8. So I printed flow rate, max flow, temperature, and pressure advanced calibration prints before getting to any bricks. Once I was happy that I dialed in the 0.8 nozzles, I was able to start printing in bulk because the main filament had actually been delivered. I had 82 old 4x2s to get through, so that's where I started, and after a few ambitious prints that were printed a bit too quick and weren't very nice, that was basically my life for like 10 days. 3D printing is cool because you don't have to make solid parts. In fact, parts can be completely hollow if you want, and that's actually what I did with this. I went to the extreme. There's 2 walls around the outside of every part, there's a very thin bottom and a slightly thicker top, but apart from that, I don't even have infill. They're completely hollow. There's 2 benefits to going completely hollow. Faster prints, because they require less material to be put down, and 2, using less material is obviously beneficial from a material efficiency standpoint. It literally uses just less filament. Little side note just to mention that I am aware of plastic waste. PLA is sort of recyclable. Everything that's clean PLA is kept. All of the packaging material, all the odd spools will be recycled, just in case you're wondering. So there's no internal support on any of these parts, which means that the inside surface is a bit funky. Anyone who knows 3D printing would know how much of like a clacky, plasticky, finger slicing nightmare it would be to have to remove support material from 500 giant bricks. I did make some adjustments in the design to make the parts faster to print. The internal sort of ceiling relative to the top surface you actually see is closer than it is if you were to scale it perfectly from Lego. That's so that it kind of does one top bridge rather than having to bridge here and then again. It's a bit faster. I also made kind of chamfers in the top corners that meant that the bridging gap was a bit smaller throughout the entire project. There was support on the small stars and a little bit on the bits that glue together, which I'll talk about in a minute. That was basically it. It was pretty economical. Naturally, this tree is almost entirely green, so naturally, almost all of the printing is green, and I printed green stuff for like 2 weeks straight. It was way more green than I can kind of even show you or get across to you. It's 2/3 of the project by numbers, but way more than that by volume. There was mountains of parts. Every single day I'd get up, change the prints over, print 3 or 4 like 4 or 5 hour prints throughout the day, stick a long one overnight and do it again. Eventually I did get through all of the green after 400 odd pieces of the stuff, and honestly that day was kind of magical.
That marks the last green piece off the P1P or X1C. The first box of not green.
Every time I could break into a new spool and open a new colour and print a slightly more interesting shape than just a regular green brick was like a little treat by the end of this thing.
It's actually a slightly less exciting colour in brown, but that's fine. I'll take it. It's not green.
I went a little bit mad, not helped by having actually quite a bad cold that my nearly qualified doctor girlfriend thought could be actual flu, like real man flu, you know? Half of November was a bit of a blur, filament, printing sounds and bogies. Despite everything going well, I had to maintain pressure because as I got through the green stuff and into some more interesting shapes, some of those were literally one-off, so there might be a complete disparity between the amount of CAD time for the part. Some stuff would take as long to CAD as it would to print. Overall, the printing went really quite well. The tolerances I was really worried about all along weren't actually that hard to hit, and I think that's because I didn't have any infill in these parts, and I think that meant that they were flexible enough that any imbalance was sort of soaked up by just flexing the shapes. So did struggle with bed adhesion a little bit. Some of the parts warped just because they're so physically big. Generally, it went pretty well. I'm pleased to say, against the odds, no glue was needed on this project that wasn't essential, and by that I mean nothing broke, nothing cracked, nothing needed fixing. We only glued stuff that was physically too large to fit on my print beds, and for those parts, basically the big bricks, I split them down the middle and made this sort of interlocking geometry that meant that gluing them was pretty straightforward. And Ruth came over around that time.
We're gluing.
Yeah.
We're glooping.
She collected those and glued them up at hers. Later on, there was one other part that needed gluing, which was the main star on the top of the tree. I tried to print that in the same orientation that I'd be printing everything else, and it warped off its supports. Lesson learned. So I decided to split that into two, print it face down, and then glued the middle bit in when we were doing the build. Right at the end of the project, I did slightly break the mould. I switched to a 0.4 nozzle on the P1P and X1C in order to print the candles, the candle flames, and a couple of the baubles. The detail towards the end was I grabbed a random Amazon brand of orange transparent PTG as against the PLA to print the candle flames so they'd let light through.
Ruth is on her way. She's going to be in about 5 minutes, and we're going to play the game of how much Lego can you fit in a Tesla. Huge pile of prints on both tables. She picked up some of the green stuff to glue a couple of days ago. Apparently that's been going well. And then I've got on these two machines, I've got the final bits of candle, so candle stems, candle flames on the X1C. Today's Tuesday. We've got a day in continuity, which is Friday, so we're going to make the bulk of the build today, and hopefully it'll look good and stuff, but then we'll probably come back to it on Friday, refine it, get some beauty shots, get the thumbnail, that sort of thing.
Starting the build meant transporting everything out of the cellar, up the trapdoor, into Ruth's car and to Ruth's living room. I don't know exactly how many parts there were at this point, but I'd printed at least 500, so it was actually quite a large logistics thing to get everything to hers. We managed it, and we laid all the parts out and just... Unsurprisingly, although kind of hilariously, we just followed the instructions to build the tree. We literally went page by page like you would the small one to make the big one. I know some jeopardy is good for videos, but I have to be honest, it went together like a dream. The whole thing just sort of clicked together exactly as you'd want it to. We did screw up a little bit, but that's different, where we place stuff down in the wrong place, and then yeah, you've got the physical fight to get it apart, unlike real Lego. Don't get me wrong, it was a lot of work, just physical labour, but it was so satisfying. The clicks and the pops and the bangs, brilliant.
Oh, the 6 of those, where do they go? A?
Yeah, I think.
Oh, do you know what?
Isn't it?
It's so solid.
It's just like a shield. We can make the most awesome full-size Lego shields.
Very satisfying.
It's extremely satisfying. I really like the way all the overhang looks as well. Just like the book says, we went layer by layer, made these all up, laid them out in the living room, and eventually it was time to slide them over the central stand that Ruth had made. It's quite pure looking. I'm not sure, is it? It might actually be a two-person job. Oh, hang on, how much are you lifting? How much are you actually... That is beautiful. The fit over the stand was awesome. I know I've said tolerances 50 times at this point, but the sliding sound it made was just... It was kind of a bit of before we knew it, yes, it took 2 or 3 hours, but we'd done it. It was not only fine, it was good. It looked awesome. It got dark in the meantime. The result is this giant, perfect scale model of the original Lego tree. And I know that was the whole point, but bearing in mind the amount of work, both sides of the equation, my side and Ruth's side, it was awesome. Basically, to see it go together and very satisfying.
Does that click? Do you do that side?
we happy with that? I think we're
think
fairly
so.
symmetrical in my shot.
It's very surreal that it's finally here.
Yeah, I was thinking like this, a lot of what I do is very kind of fleeting, like my projects are very development-y, they never really finish. The cool thing about this is it's done,
Yeah.
which is awesome. It's not a sensation I'm used to. It's like, this is finished.
Yeah, it's done.
I don't finish
Sorted.
projects, they're always rolling.
Tick.
So that's pretty cool.
We need to make more videos, so we just annoy him on
Yeah,
social media
yeah,
all the
just
time.
annoy me a lot. I'm
Yeah.
guilt-driven.
Find him on Instagram and be like, when's your next video? That's what everyone needs, right?
And it'll probably be robotics based
Yeah.
rather than Legos. The truth. Good idea.
Thanks.
From 3 years ago or whatever.
From 3 years ago.
Right then, if you've enjoyed this video, then thank you very much for watching, and if you haven't enjoyed this video, then I'm sorry. Remember, if you want to get a better understanding of the history, the very important answer to the question of why that we did this thing, watch Ruth's video. That's going to give you more of that context. I need to have a drink of water, stay hydrated, and I'll see you next time.